and reduce images. So the next step is to learn how to do photometry from them. So you can add those points to those multicolor plots, right, and see how something changes in brightness as a function of time. So for that, we have Professor Copperwheat, who is from University. The Liverpool telescope, which is a 2-meter telescope in the Canary Islands in Spain. So, Chris, please take it away.
Thank you very much. Good to go? Good. Right, okay, thank you for having me here. So, as Nancy said, I'm going to follow on directly from what Dan's been talking about. So, in the morning session, we went through the process of starting with sort of raw astronomical data towards getting an image in which you can make measurements of the individual points, and now we're going to turn that into some sort of scientific result. So this telescope is the Liverpool telescope in the Canary Islands. Not in Liverpool. In Liverpool, about sort of 360 days out of the year, it's cloudy. So our telescope is in the Canary Islands. We don't have any staff out there at all. It's fully robotic. So everyone who works on our telescope is based in Liverpool, and we run it robotically from Liverpool, which works really well for the type of science we want to do, because we're interested in rapid reaction follow-up of transients, exploding stars, that sort of thing. And so the fact that we have a robotic controller, there's no humans in the loop, means we tend to be very, very fast in following up the type of science we want to do. So it's an ideal telescope to work with the collaboration and other collaborations we have on time-domain science. Okay, so photometry is essentially the measurement of integrated flux received from a celestial target. So I say this is the most sort of fundamental measurement we can make in astronomy, really. How bright is this object? By integrated flux, I mean the counts per unit time per unit area. So here we have a zoomed in sort of one of the images we saw earlier. So this has already been debiased and flat fielded and all that, so it's ready for us to now move on to make a photometric measurement. So if we start with the basics, so these terms are sometimes used differently in different areas of science and engineering, but luminosity, we say, is the total power from a source of radiation in units of energy per second, in all directions overall wavelength, and flux is the luminosity per unit area of the source, or detected per unit area by the observer overall wavelength. So we have our source here with a radius r star, and we have an observer at a distance d. So the total luminosity is given either by this relationship here, where 4 pi r star squared, the surface area of the object, multiplied by f, the surface flux, or at a distance d. The measured flux, capital F here, is L 4 pi d squared f. So we have those two relations. We can take those and we can combine them to get this relationship, or big F over little f. The detected flux divided by the emitted flux is inversely proportional to d squared. So this is the inverse square law for radiation, which I'm sure you're all familiar with. Now in astronomy, we tend to use the magnitude system to measure fluxes. And this is highly in ultraviolet to infrared, at least. And this is for historical reasons, really. If we were to start from scratch, we'd probably do things quite differently. But this is the way we do it, and it's always down to this guy. This is Hipparchus of Nicaea, a fundamental guy in astronomy in many areas. But one of the things he did was establish this magnitude scale, and essentially he did it by eye. He saw various stars in the sky, and the brightest stars he could see these stars of the first magnitude, and then the ones who were a little bit fainter, he said stars of the second magnitude, right down to the ones right at the limit of what he could see, which he called stars of the sixth magnitude. So this is how he catalogued the stars he could see in the sky. Now, the thing is, the eye is actually a very interesting detector, a very powerful detector of light, particularly in terms of its dynamic range. Anyone who's done any photography will know this. If you go out and take some photographs, if you set the right exposure time for whatever you're photographing, a bright summer sky is completely white in the background, and if you set for the background, the foreground is too dark. So the eye has tremendous dynamic range. We tend to be able to see this automatically. We see the contrast in both the sky and the foreground. And there's an incredible brightness difference between the two. So actually these stars he had, from the sixth magnitude star to the first magnitude star, was approximately 100 times difference in terms of actual energy received. Use the eye's sort of non-linear response to light. So next person is this guy, while he was at Oxford in the time of the 19th century. he sort of formalized this to say that a 6 magnitude star is precisely 100 times fainter than a first magnitude star. So that means the difference going from first magnitude to second magnitude and so on corresponds to a change in brightness of 100 to the power 1/5 or 2.512. So this is his equation, Pogg's equation. So the ratio of the flux is F1 over F2 for two objects. Goes 2.512 to the negative M1 minus M2, where these are the magnitudes. The minus here because the brightest stars are the first magnitude stars. On both sides, 10. And then we rearrange this fundamental equations in astronomy, the magnitude equations. The difference in the magnitude of our two objects goes as minus 2.5 log to the flux ratio. So I guess one thing to make clear here is that this 2.512 is not this 2.5. I've not just rounded that down. So this quantity becomes 0.4, and we divide through by that 0.4 to get the minus 2.5 there. So this is the magnitude equation, which is the fundamental of all we do here. I'm sorry, yes?
I just want to briefly point out that there's an astonishing parallel between what this Greek astronomer said with probability theory. Because in probability theory, most distributions go from minus 3 sigma to plus 3 sigma, and it's from 1 to 100. And so, 1, and the other is a magnitude 6, which is extremely that it's so powerful.
Yeah, it's an interesting point. Yeah, So it's funny to think that the system is entirely based on. Oh, certainly. How's that? Is that better? Okay. Yes. That's an interesting comment. Yes, thank you. So yes, right. So this is something Dan touched on in his lecture, but if F here is the total flux emitted by the object, then the corresponding magnitude for that flux we refer to as the bolometric magnitude. But that's a difficult quantity to measure. If you just think of the physics of making a detector that can detect photons at both extremely short and extremely long wavelengths, this is essentially impossible. So we generally measure flux over a finite bandpass. To compensate for both the physical reality of detectors, but also, as Dan said this morning, to enable us to compare what we measure with observations made by other telescopes and other astronomers. So, for example, we have the V-band magnitude around about 550 nanometers. So we have a band pass here, a wavelength range essentially, and the F we use generally is the flux integrated over that wavelength range. There are a number of photometric systems. Again, I'll just quickly skim through this because Dan did already mention this. So we have a well-defined set of passbands and filters with well-characterized sensitivities that enable us to make these. So there are many of these. You know how it goes. Every time someone thinks up a new system, there's a new standard described, and suddenly these sort of multiplied. Everyone thinks they can do a little bit better. But the most common ones are the so-called Johnson's cousin system of UBVRI. And then that's been extended into the infrared as well. But these days, the state of the art, what most people use as the kind of modern standard is the FDSS, the Sloan Digital Sky Survey filter set. So here's the detector plane of the FDSS camera, and here are the band passes. So they are fairly broad in bandwidth, they have high transmission, and they're sort of nicely square, they don't tend to overlap. So these are very good as a sort of a diagnostic of the light when we want to cover a wide wavelength range and make efficient measurements. So those are what we call broadband filters. They tend to have passbands of greater than 30 nanometers. There are co-called narrowband filters as well, which have passbands of less than 10. So the main purpose of a narrowband filter is to isolate a particular spectral line. For example, this is a transmission curve for a hydrogen alpha filter. So this isolates the light from this particular hydrogen line. And there are intermediate bandpass filters that sort of sit between the two in terms of their width. So we go back to our magnitude equation. So the difference between the magnitudes goes as minus 2.5, the logarithm of the flux ratio. So note that this quantity is dimensionless, so we can use something like counts per second in here as long as we're making a consistent measurement for both stars. So essentially, if we have this ratio here of integrated flux of two stars, star 1, star 2, you can calculate the difference in the magnitudes. So typically what we do is we place down an aperture, and we literally are sort of counting counts per second within this aperture, which gives us a measurement of the flux. It's not really anything more complicated than that. Now, inside this aperture, you have not just the contribution from the object, but you also have a contribution from the sky, because the sky is not completely dark, so you have to account for that as well and subtract that. So this magnitude equation gives essentially the relative magnitudes, the difference between two stars, by the ratio of the fluxes. But you can take this equation. If you say we have a star of a magnitude of 0, so if I say my M2 here is a 0th magnitude star, so we can go beyond this sort of 1 to 6, because actually stars range beyond what you can see with the eye, of course. So if we have a 0th magnitude star here, then this gives you the apparent magnitude equation. So the magnitude of my star is minus 2.5 log f over the flux of that 0th magnitude star. So F0 here is the flux of my 0th magnitude star. So historically, we've defined Vega as the primary standard, the standard star on whose brightness all other stars are measured. And so we have the fluxes of our 0th magnitude star, of our Vega. And that's true also in all bands, in fact. So Vega has a 0 magnitude by definition in UV, VRI, etc., etc. So if we take this equation, we can also rewrite it as this. So I'm using my log rules to expand this out here, and calling this F0 part Z, which we call the 0 point. So here in this equation, which is just a re-expression of this, the magnitude is given by minus 2.5 log F, and we call this the instrumental magnitude of the star, and Z is the 0 point. Now, just as an aside, so Vega historically we call the absolute. No, it does vary slightly. Every star varies to some degree. So this use of Vega as a primary standard is a little bit outdated. In the modern era, the absolute reference system is commonly used, or one of the ones that's commonly used, is the AB magnitude system. So this is based on a flux measurement calibrated in absolute units rather than with respect to any particular star. So MAB goes as 2.5 log 10 of the flux divided by 3631 Janskys. So a Jansky is a unit that we've inherited from radio astronomy, where 1 Jansky is 10 to the minus 26 watts per hertz per meter squared. So this is an alternative way of defining essentially what a 0th magnitude star is, rather than referring to an actual sort of physical unit. But that's just really an aside. It's not something you need to worry about going forward. So I have this equation that I had on 2 slides ago, where the magnitude of my star is given by the 0 point and the instrumental magnitude. So this is true assuming that the instrumental magnitude and the 0 point were measured with the same instrument and in the same manner. And these are going to vary for any particular object and based on our particular optical system. So by optical system, I mean everything involved in the collection of photons. So a telescope, for example. So some telescopes are bigger than others, and some telescopes have clean mirrors and some telescopes have dirty mirrors. And then the detector will have a different efficiency depending on how it's been made and what CCD has been used. And you'll have a filter with some sort of transmission properties and bandpath and so on. And then your atmosphere as well will also depend on where your telescope is in the world. And it will also depend on what the conditions were like in that particular night in terms of the amount of dust or a water vapor in the atmosphere. So all of this affects the number of photons you're actually going to measure. And so both of these quantities are going to vary from observation to observation, essentially. So the task of calibration is to determine these properties with the aim of determining the true magnitude of the object. So for calibration purposes, again, so the magnitude goes to the 0 point and the instrumental magnitude. So essentially, to make our measurement, to calibrate our measurement, there's a 2-step process. We start by taking with a star with a known magnitude, which we tend to refer to as a standard star. So We observe our known star and determine the instrumental magnitude of that particular star. And we know this, we've looked this up in the catalogue, and that gives us Z. And once we know the 0 point of our optical system, then we can measure the flux of a second star to calculate its unknown magnitude. So it's a two-step process. We have our standard, so the flux of the standard, which we measure, and the magnitude of the standard gives us a 0 point, and then once we have the 0 point and the flux of the star, which we measure, gives you the magnitude of that star. Okay, so we calibrate our optical system with our standard, and then we can measure any star that we choose. Now, sort of historically, the way you do this is you look up a standard in a catalogue like this. This is a catalogue of known standard stars that are known to be photometrically stable and don't change. And you would observe your standard on any particular night with your optical system, and then use that as your kind of calibration. But the era of kind of wide field surveys means this kind of traditional method of photometry, where you're implementing your science exposures with lots of observations of standard stars, is not strictly necessary. And so typically people will use stars in their science exposure to calibrate their photometry, and they're able to do this because the huge sort of coverage we have of modern surveys gives us very well characterized stars in any particular science exposures. So we can use our survey, which gives us a detailed catalogue of stars, and use that to know the magnitudes of the stars in our field and use those as our calibration source. So there are many catalogues available for this type of work. So I'm just going to mention a few of the main ones. They vary by footprint, essentially, the area of the sky they cover in the filter set. So some of the ones you might commonly use are the FDS Survey, which has this kind of weird footprint on the sky, these kind of stripes at which it's measured stars. But of course it observes in the full sort of Sloan UGRIZ filter set, so it's very popular. If you happen to be coincident with a Sloan field, this is a good one to use. The Pan-STARRS PS1 Survey uses a different set of filters but covers the entire northern hemisphere. Here's a lovely Pan-STARRS image of the northern hemisphere sky. There's the 2MASS survey, which is all sky, infrared, relatively shallow, but again it's a popular source. So essentially, depending on what observation you've taken, depending on what filters you've used to make your observation, you would choose an appropriate survey for your calibration. So right at the top of this lecture, I defined photometry in this way. So the measurement of integrated flux received and assessed to your target is what we're talking about here. So there are various ways you can do this. You have point sources, they're stars essentially, and we're going to talk about aperture photometry, which is the sort of most simple method, and then point spread function photometry, which is a little more complicated. And then for extended sources, like galaxies or things like that, this is out of scope for this lecture, so I'm not going to mention it at all. But there are various techniques you can apply to look at the measurement of flux over an extended surface. So aperture photometry, the way you do this is to measure flux within an aperture, obviously. Your aperture is typically, but not necessarily circular, because your star is typically circular, but not necessarily. You might have sort of poor quality data, in which case the stars are elongated due to a movement of the telescope or something, in which case you might choose to match your sort of aperture shape to the actual shape of the star. So you measure your star flux from the aperture. Remember, this also incorporates some sky photons. You need to measure the sky flux, which is typically measured from a surrounding annulus. So the brightness of the sky will change across your field, potentially, depending on how large your field is. So by measuring in a circular annulus around you get the closest approximation of what the sky flux is actually underneath that aperture. You would ideally use the same aperture to measure flux from your standard star for the calibration. And you can compute the total flux from the curve of growth, which we'll discuss in a minute. So here we have a red aperture around our star. So the signal here is the sum, essentially, of all of the counts inside this aperture. So what you're getting, actually, when you measure that is the sum of object plus sky counts within that aperture. Then you do the same thing for your yellow annulus. So in here, essentially, you can measure a sky background per pixel. So you can count up the flux here and divide through by the number of pixels. And then once you have a measurement of the sky per pixel, you can subtract off the sky by multiplying the number of pixels in the aperture by the measurement of the sky background per pixel. What size aperture do you want to use? Well, when making any measurement, we're looking to maximize the signal-to-noise ratio. So the signal is the count you're getting from your target, essentially, and the noise comes from multiple sources. There's an equation here which we won't discuss. This is the array equation for photometry. So we have a signal term here, and then these are the noise terms that come from various sources. You have a noise term, a shot term from your sort of measurement error, essentially, in your target. You have this sort of sky term, and then these are kind of detector terms in terms of the dark current and the readout noise from the detector. So these are the sources of noise in your CCD measurement. But the sky is a contribution here, right? So the point is that if your aperture is too small, so this is an aperture that is clearly too small, so we are throwing away a large amount of signal from our object here, so that's not good. We're losing signal. Here is an aperture that on the face of it seems to be much too big, so what we're gaining here is too much sky, so we're adding noise. Okay, so both of these are suboptimum. So in practice, we find that the optimal aperture size is approximately equal to the full width half maximum of our star. So it's often, if you kind of eyeball it, you're often there or thereabouts in terms of where it is. But you can obviously measure the flux of a variety of different aperture sizes, and compute the signal to noise for each aperture size, and then pick your optimum from that just empirically. So the point here is because the optimum aperture size depends on the full width half maximum, it depends on your optical system. It depends on both the imaging qualities of your detector as well as the seeing and the conditions at your observing site. However, to measure the total flux is very difficult because there is always some light that's going to be scattered to very, very large radii. So, there's a point where your aperture it's very, very difficult to choose an aperture size that contains all of the flux, in which case it's not really possible. So here we have a bright star, for example. So this is a bit dark, so I don't know if you can see this very well, but this is from a data source. So here we have a bright star in the field, and you can see that there's a distance. This is distance here. This is a radial profile of the star. So this is sort of counts along here, and this is distance from the center of the profile. So you can see we can come out to a distance here where we've hit the kind of background level, and we can be quite happy that we've encapsulated pretty much all of the flux in that sort of distance. This is a faint source in the same field, and now it becomes a lot more tricky because we don't have to go very far before we're into this noise here, which is the background. This sort of up and down here is the sort of the sky background flux. So we lose the wings essentially of the profile inside that background regime. So this is a problem. So I'm not going to say any more than that because we're going to go through this in the workshop. But we make a correction called a curve of growth correction, essentially, to give you an infinite sized aperture, essentially, and give you a sense of the true flux from the object. So yeah, this is a similar point. So we'd use the same aperture size for our target and our standard, but this might not be optimal. So if we use different size apertures, we apply an aperture correction, essentially, a scaling factor to account for the difference in the size apertures we use between our standard star, our comparison star, and our target star. And again, this is something we will address in the workshop. Okay, so aperture photometry is straightforward, really. It's nothing too complicated. It generally works very, very well. There are some complications. Which aperture size do you use is one that we've discussed. It also assumes that your background is linearly varying. If you've got something weird going on across your field, then you're improperly correcting for the background. But the real big problem comes with really sort of crowded fields. So here, for example, it's very, very difficult to plop down an aperture at a sky annulus and be confident you're just encapsulating the flux of your target source. So how do you deal with something like this? And the way we deal with this is what we call PSF Photometry. So star, as we discussed, is a point source, and the resolution of our detectors is too low to resolve its apparent size. That's why we get a kind of extended view, because we see a spread of light due to diffraction of the aperture through atmospheric seeing and so forth. So we describe this shape by a point spread function. This describes the two-dimensional distribution of the light. So here's a representation of essentially the distribution of photons from a point source, And again, this is a plot showing you sort of counts here along with sort of distance from the centre of the profile. So we can approximate the shape of this distribution with a point spread function. So typically we use either a Gaussian or a Moffat function. A Moffat is very similar to a Gaussian, but it's been found empirically to better describe a point spread function to when you get to the wings of the detectors. So we'd use a function like this to approximate our distribution of our light from our point source. So essentially we can fit these models to the stars in our field. For PSF photometry, essentially the process we do is we use a number of stars over the field to create a model for the point spread function in that particular image. So these models, or whatever you use, be it a Gaussian or a Moffat or something else, they are parameterized in a certain way. You fit your model using the brightest stars in the field essentially, and you have an iterative process where you subtract the model from the data that you create, you refine the model to minimize the residuals, and you cycle through until you get the best fit to the profiles across your entire image. So for this model fit, essentially use the bright stars in the image. So you're assuming essentially that the PSF of your fainter stars is well approximated by the bright stars in the field, which is usually a fair assumption. There are some issues here. If your PSF cannot be described very well by these profiles, that can be an issue. A more serious issue is if your PSF varies across the detector, and this is quite common if your optics are not great, or if you have a very wide field. You might find the PSFs of your stars towards the edge of the field are different. They're sort of elongated compared to the stars in the middle of the field. So this causes a problem, and so this makes it very, very tricky to create your model to model accurately the PSF of every star in the field. And that's all I've got. So if there's any questions, let's go for it now. Sure. Yeah, this is it. So you are when you're making your model, that's the ideal assumption you want to work with, but it may not necessarily be true. So in particular with kind of very, very wide fields, or in any case really where your optics are such that as you move away from the centre of the field, you can often see this, that you see kind of a coma, and this affects the extension of your object, and so that the PSF for those objects is different to in the centre of your field. So this makes this issue of modelling a consistent PSF across the field to be very, very difficult indeed. Yes. Any more? All right then. Okay, so I'm going to hand off now to Kishle, who's going to lead us through the workshop part of this